In stats, we started sampling distributions for sample means on Monday, and I typed up this example from the book because I feel like it's an explanation of a numerical example where we have a sampling distribution. Last week we looked at sampling distributions for proportions, and this week we're looking at it for sample means. So in this one it's earnings. See here it's written the true mean amount of earnings or income or whatever is $69,750, and we take a sample of 100 households and they get a mean of $66,807, so a little under the average. I take another sample of 100, and this time I get a sample a little higher than the true mean, 70,820. And what if I do this a lot, this process of sampling? So I sample an SRS of 100 a bunch of times. The very middle of all of those means is going to be the true mean. This is a picture right here of the population of incomes on the left. It's positively skewed. And if I take a sample size of 100 and do it indefinitely, they're all going to pile up right over the true mean of 69,750. That's property 1, where mu x bar equals mu. Right here. All those dots are piling up right above or just to the left of the true mean, 69,750. The standard deviation is smaller than the true standard deviation. So look at this graph on the left. It's more spread out than the graph on the right. This one has a standard deviation of sigma. This one has a standard deviation of sigma divided by square root of n. So standard deviation shrinks when we do a sampling distribution. Lastly, that 10% rule has to be true, just like it did in proportions. This is referring to like very finite populations. So capital N is the population size, lowercase n is the sample. If I'm talking about all males that exist, or all U.S. adults, or all females, or all trucks, or whatever, and I do a measurement, that population is gigantic. We're not going to be able to take a tenth for a sample of that population. So that's not, usually that condition is not in danger of being violated. But if I'm working with like a deck of cards, or say I'm sampling from a class of students, that's very finite. If I'm sampling from, say, Lubbock High students, that's finite, because I only have around 2,000 students. If I was to sample more than 200, then I'm in trouble. All right, let's keep going. Let's talk about those first two properties and a real problem. So I guess wine gives off potentially off odors because of this DMS thing. And they've studied over time that the true mean micrograms per liter in terms of DMS is 25. And standard deviation is 7. These are population numbers right here. If I take a sample size of 10, the first question is almost too good to be true. It's property 1. Mu x bar equals the true mean, 25. Standard deviation, one little step is required. Remember, it's the true standard deviation divided by the square root of the sample size. So that is 2.2136. So that's property 1 and property 2. They're both typed on your formula sheet. It's different from standard deviation because we don't have different from proportions because we have numerical data, we have a measurement. So be aware, it's a little different from last week's stuff. The next problem, we didn't get all the way through in class. We started it, so I'm just going to start it and, well, I don't know. We'll see what the timer's at when we finish. I think I asked part A last semester. This looks very familiar. Height of young women are normally distributed with a mean of 64.5 and standard deviation 2.5. What's the probability that a random woman is taller than that? And look at part B. What's the probability that the mean height? Well, let me circle SRS of 10. Mean was important also. But two different questions, but yet they look very similar because they're both looking for a probability greater than 66.5. So be really careful. Make sure you note that this one has a sample size. This one above it on part A, there's no sample. We're just looking at one woman. So we start on part A just like we did in the fall. And we say X is normal with a mean of 64.5 and standard deviation of 2.5. Remember that those were points right there. You had to define the distribution. Then you had to write it in terms of a proportion, and I wanted that. And then we did a z-score. I think it's 0.8. And then you can just write the answer if you know how to use normal CDF. I'll write normal CDF here, but you don't have to. If you've written all that stuff I just wrote, you don't have to write this. So the lower is 0.8. The upper is infinity. Leave the mean and standard deviation alone because we got a z-score. We want to leave those alone. The final answer would be 0.2119. All right, things change on part B. We are now looking at a sampling distribution of X bar. The mean stays the same, which is kind of weird. That doesn't change, but the standard deviation changes big time. You divide by the square root of the sample size. And we get 79.06. Let's say something about the shape. Up on part A, I said it was normal. This one is also normal. Because the population is normal. People struggle with this because after this slide, we talk about the importance of a large sample size, 30 or greater. And that makes it normal. But yet, if the population is normal, look up at the very top of the page, you don't need a large sample to force it to become normal. It just naturally is. So, since the population was normal, this one's normal. All right, we just said it's normal. Let's do another z-score. It's going to look really similar at first. Oh, I forgot one more thing. You got to write it in proportion form. No longer are we talking about just an x, but an x bar. It's so weird because the question looks the same, but yet we're going to get a different result because of that standard deviation. So this time we're dividing by 0.7906, and that z-score is going to be further to the right on the z-curve. We get 2.5297. So for that final proportion, I bet it's close to 0. Very rare. A mean of 66.5 or greater should not happen. But yet one woman being that tall or taller is not rare. Kind of interesting. Look like similar questions, but yet very different. See y'all later. Bye.